Welcome to Empowered Learning. This is the second video in the video series on techniques of integration, where we are addressing the technique of trigonometric substitution. So in the part one video, we started off with the basic idea that we're using some of the trigonometric identities that we know of, mainly the one that comes from sine squared plus cosine squared equals 1, and the variations on that. We're exploiting that to be able to do some substitution for things that are hard to take the antiderivative of algebraically. We put it in trigonometric form to make it easier for us to deal with, and then we convert back into algebraic form once we're done. So this is the first of the last three examples that I wanted to do for you here. So we're going to go ahead and get started on this one. So we see here, since we have this square root of 4 minus w squared here, that this particular integral is sort of taking on the form that looks something like this. Okay, so it's kind of taking on this form here. And we know whenever we see square root of some number squared minus a variable squared there, that we have a choice into either saying, in this case, letting w equal a times cosine theta, or we can say let w equal a times sine theta. Okay. What I'm going to do is I'm going to choose using w is equal to a times sine theta for this one. Okay. And I'm doing it just to be a little different because I know I've worked this problem out before and I've used it with cosine. So I want to do it with sine just to show you that we can use the different substitutions, but yet we still get to the same answer here. So I'm going to erase what I have here for the w is equal to a times cosine, and then we'll start this problem. All right, so with us using this suggested substitution of w is equal to a times sine theta, we need to identify what a is here. And we know since a squared is the same as 4, that a is going to end up being 2. Okay, so I'm just going to go ahead and replace that with this 2 here, so we don't have to think about that anymore. And so now we know that since we know what w is, we're going to have to figure out what dw is, which is just going to be the derivative of this times d theta. So this will be 2 cosine of theta d theta. And also note that in addition to the dw and the square root of a squared minus w squared here, I also need to figure out what w squared is. And of course, w squared is just going to be 2 times sine theta quantity squared, which is just 4 times sine squared theta. Okay, so now that we have all that, we can now come here and replace everything. And I'm going to switch colors here to show that we're actually starting that process. So this will be integral of 16, and in place of dw, we're going to have 2 times cosine theta d theta. We're going to divide that by w squared, which is just 4 times sine squared theta. And then multiply that times the square root of a squared minus w squared. So square root of, we know a squared is 4. When we know w squared is just going to be 4 times sine squared here. So now we can just simplify what we can here. I'll go ahead and simplify as I go. So we know 16 divided by 4 is just 4. Okay, and of course 4 times 2 is going to be 8 here. So we'll just say now we have integral 8 of cosine theta d theta. And in the denominator here, we'll still have this sine squared theta. But now we see that this 4 minus 4 sine squared, we could rewrite this as 4 times 1 minus sine squared theta. And of course, that 1 minus sine squared theta, that is just going to be, all this is just going to be cosine squared theta. Okay. So carrying on here, we'll end up having integral 8 cosine of theta d theta on top. Still have the sine squared theta on bottom. But now, since we just have 4 times cosine squared theta, and we want to take the square root of that, that is just going to be 2 times cosine theta. And so now with that, we know that this cosine and that cosine will reduce to 1. And this 8 and this 2 will just reduce to 4. And so now what we have left is just 4d theta divided by sine squared. And of course, 1 divided by sine squared is secant squared. Okay. And so now at this point, we're sort of on easy street because of the fact that we do know that the derivative of cotangent is negative cosecant squared. So that means that the antiderivative of a positive cosecant squared will just be a negative cotangent. So we can go ahead and say this is negative 4 cotangent theta plus c. So now at this point, we're happy that we got this answer here, but we are not done yet. Okay. And we know that we're not done yet because this answer is in terms of theta. We need the answer in terms of w. So we need to make that connection there. And so if you recall, we had that w was equal to 2 times sine theta. Okay. But what that tells us here is that sine theta is actually equal to w divided by 2. And let's clean that up a bit here. And so we can do our whole right triangle thing again. So if we're looking at this, we call this angle theta. Then, of course, sine is going to be opposite side over hypotenuse. And I could figure out what this side x would be here. And that would tell me that, let's say, x squared plus w squared is going to equal to 2 squared, which is 4. And this would basically just tell me that w is 4 minus w squared here, okay? Which, of course, we see that's what we have there. So now that we know what w is, excuse me, we'll go ahead and substitute this back in. So what we'll do here is just do a different color. Kind of come back here and say, all right, well, this is just square root of 4 minus w squared. And so now that we have that, we need to be able to express cotangent in terms of w, basically. Okay. Oh, my bad. Yeah, I did the wrong one here. Sorry. Yeah, this should be here. So let me go ahead and draw this. So, I'm sorry about that, you all. So this should be w here, and let me get this color back. Yep, that should be here. So that's what we want to replace. And yeah, I see why I did it wrong here, because I labeled it W instead of X. And it should have been X. Yeah, so that's what we should have been doing. So from here, we know cotangent is just the reciprocal of tangent. And if tangent is going to be opposite over adjacent, then it means cotangent is going to be adjacent over opposite. So now we just need to rewrite cotangent as just square root of 4 minus W squared, all that divided by W. And so that would be our final answer there once we do that. So let's switch colors here. So therefore, you know, cotangent of theta is just going to be square root of 4 minus W squared all over W, which implies that -4 cotangent theta plus C is just going to be a -4 times square root of 4 minus W squared over W plus C. And of course, that is going to be our answer, which is going to be equal to our original problem here, which was the integral of 16 dW over W squared. And this is W of 4 minus. Yeah, so let me erase that. 4 minus W squared. Yeah. So that is our final answer for that one. Okay, so for our next example, we see that we need to take the integral of 1 divided by square root of t squared minus 6t plus 13. And so in looking at the square root portion of our integral, it doesn't really look like something that we're used to dealing with, but the fact that we have a quadratic expression in our radicand, that expression under the radical, we know from pre-cal here that anything that can be expressed as ax squared plus bx plus c in quadratic form could also be forced to look like this. In other words, forced to have one of the terms be a perfect square. And so if we force this quadratic expression to have a perfect square in one of its terms, then it will match the profile of what it is that we're looking for as far as one of the suggested trig substitutions that we're after. And so we'll actually have to transform it from what's called a canonical form into the vertex form for us to be able to do that. Now, of course, the process of doing this, the traditional way of doing it is called completing the square. And so that is what I'm going to do. For those of you that don't necessarily remember completing the square, you can cheat. And the way that you can cheat here is that your h is just going to be a negative b over 2a, and your k is just going to be f of whatever h is, or you could write it another way, 4ac minus b squared all over 4a. Okay, so if you just pick what a, b, and c are and plug it into these formulas here, you'll get it. You'll get exactly what it's going to be here. Now, a is still just going to be whatever a is. So in this case, a is 1, so it's just going to stay that way. But for the rest of these, you can just say, let's say minus a -6 over 2 times 1. You'll get that answer, and then of course you'll plug in a is 1, b is -6, and c is 13 into here and figure out what that result is. I'm actually going to do it the more traditional way, but for those of you that want to cheat, you could do it this way, and you can still get to the same thing that I am going to get to. Okay, so I'm going to go ahead and erase this and then actually start breaking this down so that we can get it into a form that's good for us doing the traditional completing the square method. All right, so first thing that we're going to work on is trying to get this quadratic expression here into the vertex form via completing the square. So how we're going to do that is separate those first two terms. We're going to introduce a third term here. And since we're going to have an understood 1 times whenever this is, we're going to subtract by the same exact thing. So now, in order for us to employ completing the square, what we need to do is we need to take this middle number here, the -6, we need to divide it by 2, and then square that result. And we're going to do the same exact thing here. Okay? So in us doing that, we'll have t squared minus 6t plus -6 divided by 2 is 3, and 3 squared is 9, plus 13, and of course we'll get the same thing there, 9. And we know here that this is going to be a perfect square, and this will factor into t minus 3 quantity squared. So we got t minus 3 quantity squared here, plus, and 13 minus 9 is going to give us a 5 there. Excuse me, I mean 4 there. Yeah, that should be a 4. All right, so once we have this in this form here, then we see that this sort of fits one of the profiles that we were looking at as far as the trigonometric substitution here. And I'm just going to kind of write it here. Forget about the square root right now. But this will sort of mimic the x squared plus a squared situation here. Okay. And so here we can let x be t minus 3, and we can let a be 2. So here x would be t minus 3, a would be 2. And so also with this situation here, we know that this also mimics, and I'm going to do this in a different color as well, this also mimics tangent squared of theta plus 1, okay? Where this a squared here is just going to be some number. And notice here that we have something squared plus number squared, okay? And if I wanted to balance it with the a, I would just have a squared here, and this would just be a squared there if I wanted to balance it out. So my point here is that with this x being here, this could be t minus 3, but this also could be a times tangent theta, okay? Because remember, this could be written as a times tangent theta quantity squared plus a squared, okay? And so the suggested substitution for this is going to be to let a, which in this case is going to be 2, times tangent theta. So this will just essentially be 2 times tangent theta here, okay? And so that is going to be our suggested substitution. So the thing that looks a little weird here is the fact that we already have this t minus 3 here. So it's like we have to do another substitution before we get to the substitution that we want. And you can kind of handle that, how you want to. The way that I'm going to do it is, since I know that t minus 3 is in the place of x, and I know that that t minus 3 is eventually going to have to be 2 times tangent theta, I'm just going to start off with what I'm going to end up with and just deal with it simultaneously here. So I'm just going to say, hey, rewrite what I have here in terms of this t minus 3 squared plus 4, and then afterwards say let t minus 3 be the 2 times tangent theta, and just deal with it from there. So that is what I'm going to do here. So we'll have this, and we'll say this is square root of, and this will be t minus 3 squared plus 4. And instead of writing 4 there, I'm just going to put 2 squared just so that it's obvious that a is 2. So we're going to have that. And so now that we've done all this heavy lifting here, again, we know that t minus 3 is going to be equal to 2 tangent theta. And from that, we're going to replace everything else in terms of theta here. Okay. So I'm going to go ahead and kind of section this off here. And then just continue to work on this problem. And so I'll switch colors here. And we'll say let t minus 3 equal tangent of, 2 times tangent theta. Okay. And so if we do that, then of course we need to figure out what dt is going to end up being. So if we do this, we are going to have to take the derivative of both sides, and we're going to have to take the derivative of both sides with respect to t so that we can get the dt part that we need to solve for. Okay. So here, I'm going to take the derivative of the left side with respect to t, take the derivative of the right side with respect to t. Of course, on the left side, since the variables match, we just take the derivative normally, and so we'll just get 1 there because derivative of t is 1, derivative of any constant is 0. On the right side, since our variables t and theta don't match, we'll have to use the chain rule there. So we'll ignore the 2, and the derivative of tangent theta will be secant squared theta. But now we'll have to take the derivative of the inside function, which is theta, and we assume that theta is a function of t. So we can just write it as derivative of theta with respect to t there. And so with that, we know that we can just solve for dt by multiplying both sides by dt. We'll end up getting 2 times secant squared theta d theta. And so that will be what our dt is. And so now that we have all that in place, the last thing that we want to do here, and I'm going to do this in a different color as well, is let's go ahead and simplify what our denominator is going to be there. Okay. So again, if we replace t minus 3 here, I'm just going to replace t minus 3 with 2 times tangent theta, then we're going to have basically, and I'll just write it because it may be better for me to write it than to say it. So here, if I have square root of t minus 3 squared plus 2 squared, and I replace that t minus 3 with 2 tangent theta. All that squared plus the 2 squared there. Then that's essentially just going to be 4 times tangent theta squared plus 4. And I could rewrite this as square root of 4 times square root of tangent squared plus 1. And of course, square root of 4 is just going to be 2. And we know here that tangent squared plus 1, that's just going to be secant squared theta. And square root of secant squared theta is going to be absolute value of secant. But if you remember in the part 1 video, we're going to assume that we're always looking at the non-negative option here. So that's just going to be 2 secant theta. Okay. So this whole entire denominator that we see here is just going to be 2 secant theta. Our numerator is going to be 2 secant squared theta d theta. Okay. So we'll go ahead and put all that in now. So here, all of this is going to be 2 secant squared theta d theta. And all of this is just going to be 2 secant theta. Okay. So now that we have all that in play here, we can go ahead and actually get down to doing what we need to do for this problem. So we have this. And so now all that is just going to be 2 secant squared theta d theta all over 2 secant theta, an integral of that. Let's make sure I wrote everything. Yep. And so, of course, we see that all that just simply simplifies to just a secant theta d theta. Now, at this point, you may or may not know what the antiderivative of secant theta is, but it is natural log of absolute value of secant theta plus tangent theta. Go ahead and put the plus c on the end there. Now, this is a well-known antiderivative, but it's not one that is necessarily easy to get to. There's a couple different ways that you can do it. One way is if you use some slick algebraic manipulation. You can basically rewrite secant in such a way to where you have a quotient where the numerator of the quotient is the derivative of the denominator. The other way that you can do it, you still use some algebraic manipulation, but you're basically using trig identities. And at that point, you'll have to do some partial fraction expansion for you to be able to do it. And so normally, whenever we are in teaching this particular type of technique, you haven't necessarily covered partial fraction expansion yet, so I'm going to steer away from that. But I will show you the other way of how we get this particular antiderivative once I'm done with this problem. Okay, so let's go ahead and finish up now. So our answer in terms of theta is what this is. Okay. However, we need to have our answer in terms of t. And so if you remember here, we let t minus 3 equal 2 times tangent theta. So we're going to use that and rewrite what we have so that we can figure out what secant and what tangent is as well. So here, if you recall, we let this substitution be. So that means that t minus 3 over 2 is just going to be tangent of theta. And if we look at a nice right triangle here in quadrant 1, then we know tangent is going to be opposite over adjacent. So this will be t minus 3 here. This will be 2. And so now all we need to do is find out what our hypotenuse r is. And of course, we can just do that by squaring both of the sides there and then taking the square root. So if we do that, this will essentially just end up being the square root of 4 plus t minus 3 quantity squared. Okay. Now, that should look a little familiar to you because 4 plus t minus 3 quantity squared is essentially what we had in our problem here, okay? So if you remember this, here is this t minus 3 squared plus 4, which is 4 plus t minus 3 squared, and square root of that. So it's another way of saying that is that what's under the radicand is this, okay? So here we know that our hypotenuse is essentially just going to be the square root of t squared minus 6t plus 13, okay? It's the same thing. So now that we know that, we can take our answer here and just write it and read our right triangle here and figure out what secant and tangent are going to be. So therefore, dt over t squared minus 6t plus 13, that's just going to be equal to natural log of absolute value. Secant is going to be the reciprocal of cosine. So cosine is 2 divided by our hypotenuse. So that means secant is going to be our hypotenuse divided by 2. So I'm going to have square root of, and I'm just going to write it in this form, t squared minus 6t plus 13, all of that divided by 2, plus, and now tangent, of course, we know it's just going to be t minus 3 divided by 2. And then we'll do the plus c on the end. So this is an acceptable answer. It's not the most simplified answer, but it is an acceptable one. If you wanted to get more simplified here, what you could do is, since both of these fractions here have the same denominator, you would just write all this over 2. Write that over 2 like this. And then, of course, we can use our log properties here to just rewrite this as natural log of absolute value of the numerator minus natural log of absolute value of 2 plus c. And we could replace all of this c minus natural log of absolute value of 2, all of this could just be one other constant here. So our final answer could be written like this. Pen got away from me there. So square root of t squared minus 6t plus 13 plus t minus 3 there. And then we'll say plus c prime, where c prime is just c minus natural log of 2, basically. Okay. So this would be your most simplified answer to this particular problem. So to end this video, I'm going to kind of go back and show you how we could actually come up with this particular antiderivative here, just in case you're interested in seeing that. All right, so one of the ways that we show what the antiderivative of secant is, which is natural log of absolute value of the sum of secant and tangent, is we can start off by rewriting secant in this fancy way here. And so if you look here, you'll see that we're just going to say this is secant times 1, but we rewrite secant this way, okay? And so the reason it's written that way is because if we take the numerator and multiply it times secant, then what it turns out is that this denominator here, when we take the derivative of it, it actually ends up equaling whatever the numerator is here. And so I believe whoever did this, they kind of did a whole bunch of trial and error and then just kind of, bumped into it and was like, oh, look at this. And then now you got your way of rewriting secant in a way to where you can, use it this way. So anyway, so we know here that the derivative of secant plus tangent just ends up being this. And thus we can use u substitution there. So if we have u substitution where u is going to be secant plus tangent, then we have the situation here where all of this is u and all of this is du. So we got u du here. So that makes doing the antiderivative real simple, because we know the antiderivative of 1 over u is just natural log of absolute value of u. And then we substitute back in what u was and we're done. Okay. And so what I was alluding to here is that there's another way that we can actually do this and a little bit more organically. And here it involves us starting off by rewriting secant as just cosine over cosine squared. And then from here, notice that we could rewrite all that this way. And by doing what's called partial fraction expansion, we could take this quotient and write it into the sum of two different quotients. And so what partial fraction expansion does is it gives us a method to be able to find out what a and b are. And then from that, we could go ahead and move forward and figure out the antiderivative of each of those expressions separately with the a and the b in it. And then from that, we would back into this particular answer here. Okay. All right, so this concludes the second video. I do have one other example that I want to do, and so I think that one's going to take a little while because I'm going to do it two different ways. So I'm going to go ahead and stop this video now, and we'll go ahead and move on to that third video to finish out this particular topic. So I hope to see you there.